All right, so welcome back. What's already the, final afternoon of the conference. And we'll start with one more software demonstration. So Benjamin Hackl will tell us about rigorous analytic combinatorics in several variables in SageMath.
Thank you very much. I hope, the mic is working. I want to thank the organizers as well for giving me the opportunity to give this short advertisement, basically, for something that I hope might make the lives of some of you here a little bit easier. We've learned from, let me say this. So this is one slide where you get to figure out whether this is something that's relevant for you or not. In the software I want to present for a Sage package, which can do the following: given multivariate, rational, and combinatorial generating function, which means that, rational, we've learned from Sarah before, is very nice. We'll stick to that. Multivariate makes things a little bit more complicated, and a little bit actually means a lot more complicated in the world of generating functions, but and combinatorial means that if your function that you found somewhere belongs to some concrete applications where your coefficients actually enumerate something, then you're good. So it means positivity of the coefficients. If all of these three criteria are met, then you have a nice generating function, and we give some directional vector. And what the software can do is, in considering some mild assumptions on the shape of the function, it can output the asymptotic expansion for your diagonal that you're interested in of your function. So this is supposed to be an interactive thing. So I've prepared some examples just to show you how it works, and then given there's maybe some more time left, I'll show you why it works, and I will sweep all of the nasty details under the rug because, there's not so much time right now. So if you want to follow along, if you want to look at it, I have prepared a short link for it. You can just type in bhackl.dev/asi, and you will get taken to some sort of interactive environment where you can just execute the cells. If you're lucky. If you're unlucky, then it gets stuck, and you have to use the second link to just look at the notebooks. Sorry. So if it loads correctly, and let me maybe increase the font size of this a little bit. Sorry, should have done that earlier. Maybe I managed to do so. Plus is here, right? Okay, can you read this as is, kinda? Yes. Okay, good enough for now, sorry. So after, I should have maybe said this as well, in case you want to try this locally in your installation of Sage, which some of you might have on your laptops right now, you just type in sage -pip install sage_ACSV, ACSV standing for Analytic Combinatorics in several variables. And you can also look at the package source on GitHub. Everything is open source. If everything works out and you have an environment where this package is installed in, you can just go and say you want to import one main function from the package, called the diagonal ASI function, and this will do all of the work for you. I'll just make sure that the output of this notebook is typeset, and then I'll show you one example. So an easy one is, for example, this rational generating function 1/1 minus x minus y, which is, it's not hard to figure out that this is the generating function for binomial coefficients. And so what we can do is we can just ask for the asymptotics of the binomial coefficients in some direction. You can specify the generating function just in terms of a symbolic expression, so variables x and y. I'll write just a classical 1/1 minus x minus y. I'll specify the direction I'm interested in, and I ask for something that we've called asymptotic output, and it will give you a warning, because we use something that's a bit experimental, but also the result. So this is not the classical problem with demonstrations, no. So we see the asymptotics in the form of 4 to the n to the minus 1/2, and the constant 1/square root of pi. This is here, including an error term. We can also ask for asymptotics in different directions other than the classical 1/1 direction. For example, 37 and 5, which is maybe nice because it sums to 42. We've learned about 42 this conference, so this is the asymptotics for binomial coefficients in this direction. Or, today is July 21, so why not go into the direction of 21/7? You can certainly do that as well. And there's the result. So you get instantaneously almost the asymptotic expansions for all of these. One more example that's maybe a little more interesting, other than the standard binomial coefficients, is this multivariate generating function that has been used by Apéry in his proof for the irrationality of zeta of 3. And if we just take this generating function here, we can again plug everything in. You can trust me that I typed this one here correctly down here again. And I can ask for the corresponding output, and it will tell me, well, some constants, or it looks like numerical constants. It's actually not. It's algebraic numbers. So everything is known exactly. There's no noise in terms of numerics here. And you can even ask for these, ask for a radical expression for these algebraic numbers just by pulling apart the result, basically, which you can do. There's an output format for that, and then multiplying everything together manually while asking for the right things. So here is the main term of the asymptotics after just a little bit of computation, without much effort, just from the generating function. Again, we did not need to specify anything else, no need to specify where the critical or where the contribution comes from exactly. All of this is done automatically. One final example, because it's very nice, and we've seen a bunch of lattice walks today, so I thought I'll include one as well. The Lanois numbers count the number of lattice paths in an m times n grid, reaching from 0, 0 to mn, where you're allowed to use the east step, north step, and northeast step. If you look at the generating function of those, it's not maybe immediate to see, but you can figure out quite easily that this is this. And we can, again, just extract the asymptotics with one press of a button. And then, just for the sake of something failing in this presentation, I've also included one example where we know that there's no suitable point to grab the asymptotics from. Maybe just a few more words on why this actually works, but again, I'll sweep all of the details under the rug. We have this representation of a rational generating function. We want to do or basically what the idea is, we want to do the multivariate Cauchy integral formula, which is, and then what you do in the univariate case, you expand the contour of integration, go and collect residues. You can still do that in the multivariate case, but it's hellishly more complicated because the geometry of the singularity, because it's basically a variety, and well, it's more complicated to extract the correct residues from there. So we need some sort of way of identifying the correct points or some way of identifying points that actually yield the contribution that we want. And under some mild conditions on the numerator on the denominator of the polynomial, we can actually do that. So this is work in particular done with Pimentel, Wilson, and Baryshnikov and Pimentel. And the conditions, I sweep them under the rug, I mentioned. So this is the theorem that actually tells you, given that everything is nice, how the asymptotics look like. This is something that's more or less well known at this point in the context of analytic combinatorics in several variables. And there's a nice new edition of a book by Pimentel, Wilson, and now also Melcher, where these things are treated at a little bit more length. And then the main contribution of this software basically is the implementation of an efficient algorithmic approach to get all of these things. So these critical points that actually contain that correspond to the main contribution from which we can extract it, we compute those with some sort of all-in-one strategy that is an effect of or side product of work by Melcher and Salvi. Where they encoded the solutions of this polynomial system in a certain way that's particularly nice for us to use in some sense. I'll stop here because I don't have much more time, and I hope you find this useful. Thank you. So the question is whether this is part of the current Sage release. The answer is no. It's a separate package, which is why you need this. It was there. This command here, so sage -pip install sage ACSV to get it included. There is some sort of implementation of multivariate asymptotics in Sage, but this works a different way, and we would like eventually to replace the current existing implementation with this approach because it's better overall.
Well, let's first, yes, please.
Does your program compute higher order terms in the asymptotics or just the first term?
Not yet, but more terms are possible, so it's just a matter of implementation, which is not done yet.
Okay, well, two last quick questions. Yes.
Yeah, it seems like a lot of this is sort of depending on being able to frame your number sequence as like a diagonal of something, which is a technique I haven't encountered too much. Do you know of any sort of source or paper or something that has like some examples of it or an overview of the technique or something like that?
So in general,
quickly summarize the question.
The question is, this method relies on extracting diagonals from generating functions, and where there are some references for books or anything. Basically, the resource I've mentioned, so there are many combinatorial contexts where your sequences of interest can be extracted as diagonals. Lots of things actually in walks in the quarter plane. They are very much present in that context. But take a look at the book by Pimentel, Wilson, and Melcher, and you will find lots of examples in there.
All right, to finish it off, Arvind, again.
Just to clarify, any rational, this works for most rational functions?
It works for the nice ones. So
can you maybe repeat?
The question whether it works for all rational functions, the answer is for the nice ones in the sense that there can't be anything that goes too bad with the singularity. So we don't allow like a multiple pole. The poles of the rational function have to be simple.
Okay, well, I think time's up, so let's thank the speaker again.